If someone says the Earth is a sphere, they are basically right. If a geodesist says the Earth is a sphere, they are being suspiciously lazy. Our planet is round enough to look like a ball from space, but measured carefully, it is squashed, bulging, bumpy, and even slightly changeable. So what shape is Earth exactly? Start with the simplest answer: a sphere. For navigation, school diagrams, and most everyday calculations, that is a perfectly useful approximation. Earth is about 12,700 kilometers across, so even Mount Everest is tiny compared with the whole planet. Put a bump only a few millimeters high on a basketball, and you get the general idea. The mountains feel enormous to us because we live on the surface, not because they dramatically deform the planet. Now spin that basketball. Earth rotates once roughly every 24 hours, and that rotation matters. Material near the equator is moving around the planet's axis faster than material near the poles. Over geological time, the rotating Earth settled into a shape that bulges slightly around the equator and is slightly flattened at the poles. Geometrically, the standard approximation is called an oblate spheroid, or more precisely, an oblate ellipsoid of revolution. The numbers make the distortion easier to grasp. In the WGS-84 reference system, used for global positioning and mapping, the equatorial radius is 6,378.137 kilometers. The polar radius is about 6,356.752 kilometers. That is a difference of roughly 21.4 kilometers in radius, or about 42.8 kilometers in diameter. Big enough to matter for precision, tiny compared with the size of Earth. A globe sitting on a desk will never show that difference accurately. If you made a classroom globe 30 centimeters across and preserved Earth's flattening at the same scale, the difference between its equatorial and polar diameters would be only about 1 millimeter. You would probably miss it while wiping dust off the plastic. People were arguing about this centuries before satellites existed. One way to test Earth's shape was to measure how much ground corresponds to 1 degree of latitude in different parts of the world. If Earth were a perfect sphere, the geometry would be simpler. On a flattened planet, the length of a degree changes with latitude. 18th century geodetic expeditions made these difficult measurements with chains, sighting instruments, triangulation, and a lot of travel. Measurements near the equator helped confirm that Earth is flattened at the poles. Today, a satellite can make the whole exercise feel almost unfair. Here is another way to feel the scale. The WGS-84 flattening is about 1 part in 298. That does not sound dramatic because it is not. If Earth were a perfectly round orange 10 centimeters wide, the corresponding flattening would be only a fraction of a millimeter. The phrase, "not a sphere," sounds much more dramatic than the actual deformation looks. This creates one of the best geographical tricks on the planet. Mount Everest is the highest point above mean sea level, at a little under 8.85 kilometers. But Everest is not the point on Earth farthest from the planet's center. That title goes to the summit of Chimborazo in Ecuador. Chimborazo is much lower above sea level, but it sits close to the equator, on top of Earth's equatorial bulge. NASA notes that its summit is more than 2 kilometers farther from Earth's center than the summit of Everest. So highest depends on what you measure. Highest above sea level? Everest. Tallest from its base? Mauna Kea is a famous contender because much of it is underwater. Farthest from Earth's center? Chimborazo. Same planet, 3 different answers, all reasonable once the reference point is clear. Fine, but even oblate spheroid is not the final answer. Open a GPS app, and it can tell you your position with numbers that look absurdly precise. Underneath that simple blue dot is a mathematical model of Earth. Systems such as WGS-84 use a smooth reference ellipsoid because a smooth surface is convenient. You can define latitude, longitude, and altitude on it without trying to describe every ridge, canyon, building, glacier, and wave. The physical Earth, of course, refuses to be smooth. Mountains rise, trenches sink, ice sheets load the crust, ocean water moves, and the density of rock inside the planet varies from place to place. If you literally asked for the shape of the solid and liquid surface, you would end up with a fantastically complicated object. Every cliff and valley would count. Every changing shoreline would be part of the answer. Geodesists, therefore, use another surface called the geoid. This is where the topic becomes a little weird, because the geoid is not simply the visible surface of the Earth. It is an equipotential surface of Earth's gravity field that closely corresponds to global mean sea level. In a simplified thought experiment, remove waves, winds, tides, and currents, let the ocean settle under gravity, and then imagine that level continuing underneath the continents. That reference surface is close to what geodesists mean by the geoid. Gravity is not exactly the same everywhere. A mountain range contains extra mass. Dense rock below the surface can change the local gravitational field. Large-scale variations in Earth's interior matter too. The ocean, therefore, does not settle onto a mathematically perfect ellipsoid. Its gravity-defined reference surface gently rises and falls. You may have seen pictures of a wildly lumpy, potato-shaped Earth, often colored red and blue. Those images are useful, but easy to misunderstand. They usually exaggerate the geoid's vertical differences enormously so we can see them. NOAA even warns that its printable geoid model exaggerates the bumps. Earth does not look like a cosmic potato from the moon. From far away, it still looks extremely close to a sphere. Take away that exaggeration, and the geoid's deviations are small on a planetary scale. NOAA describes permanent hills and valleys in the ocean's surface caused by gravity variations that can exceed 300 feet, around 90 meters. Compare that with a planet whose radius is roughly 6,371 kilometers. You need amplification to make the geoid's wrinkles obvious in an illustration. That sounds minor, but it matters. Suppose a surveyor wants to know the elevation of a road, bridge, or flood barrier. A satellite navigation receiver naturally works with the reference ellipsoid. But people usually care about height relative to something like mean sea level. To convert between those ideas of height accurately, geodesists need a model of the geoid. The difference can be tens of meters depending on location. A number from a GPS receiver is not automatically the same thing as the elevation printed on a topographic map. There is another complication. Earth's shape is not frozen. Tides deform the oceans and even the solid crust. Tectonic plates creep. Large earthquakes can shift the ground. Volcanoes build and collapse. Ice sheets melt, unloading the crust, while water is redistributed around the planet. Some regions are still slowly rebounding after the enormous weight of ancient ice sheets disappeared. NOAA describes Earth's shape as unique and ever-changing, not a fixed geometric object. A survey marker hammered into rock looks permanent. Then you return years later with precise instruments and discover that the coordinates have moved. Sometimes the marker moved because the tectonic plate carried it. Sometimes the reference frame itself has been updated because measurements improved. At ordinary human scale, nothing dramatic happened. At centimeter-level geodesy, the planet never really sits still. So which shape should we call the real Earth? It depends on the job. A sphere is excellent when precision is modest. An oblate ellipsoid is the workhorse for mapping, satellite navigation, and coordinate systems. The geoid gives a gravity-based reference connected to mean sea level, and the actual physical surface includes every mountain, trench, glacier, and changing coastline. There is no contradiction here. Models are tools. You pick the simplest one that is accurate enough for what you are doing. And that is why saying, "The Earth is not a sphere," can be both scientifically correct and deeply misleading. It does not mean the planet is flat, cube-shaped, or visibly deformed. It means that once you measure a nearly spherical planet precisely enough, the small departures from a perfect sphere stop being small problems. They affect coordinates, elevations, satellite orbits, surveying, ocean science, and the answer to something as simple as which mountain is farthest from the center. From a few million kilometers away, Earth is a blue ball. From a geodesist's desk, It is a rotating ellipsoid wrapped in a gravity field, covered by moving topography, and changing by millimeters, centimeters, and sometimes meters. Both pictures are true. The difference is how closely you look.
Thanks for watching! If you enjoyed the video, please like, subscribe, and leave a comment below. See you in the next one!